So this week we're going to talk about forces, and by the end of part 1 and part 2 of our lectures, you should be able to define force, classify them. We will discuss friction forces, weight, and determining the resultant of two or more forces. You should also be able to divide forces into their respective components depending on the situation, as well as determine any unknown forces acting on an object, especially if they are not equal. So force is defined as a push or pull exerted by one object on another object. Force pairs are equal in size but act in opposite directions on an object. Forces cause or tend to cause an object to accelerate, so it causes it to either start, stop, speed up, slow down, or change direction. And two different units that are used for force are the pound in English, but as we have discussed prior to this chapter, we will discuss forces in the unit of newtons, where there is a mass and an acceleration within this component. So force is a vector quantity, so it does have a magnitude, which is the size of the push or pull, and a direction, or the line of action. Now, the one thing that's very important that we will discuss throughout this chapter is the point of application on an object, because as we know, for instance, if we have a box sliding along a floor, a point of application here would deliver a different acceleration of this object versus if the point of application was in a different spot, as in this second placement. In the first slide, I discussed force pairs, and this is a good depiction of these pairs acting in opposite directions. Here, the force acting on the shot putter is going to be the weight of the shot put, while the force acting on the shot is going to be the muscle pull, or the muscles that pull and create a force and change in acceleration of these segments to propel the shot upward and forward. So again, a force is a vector quantity that requires a magnitude and direction. Force is represented graphically with an arrow. Now, different characteristics of this arrow will determine how a force is distributed, the magnitude of the force, and the direction. So the length of the arrow represents the force magnitude. So if you have an arrow that is this long compared to this long, arrow number 1 will have a higher force or a larger magnitude than arrow number 2. The shaft of the arrow, so the line itself, indicates the line of application, so where that force is actually applied to an object, and one end of the arrow indicates the point of application on the object. So the end of the arrow with actual arrow on it, not this end, of course, is going to indicate where that point of application is applied. Some assumptions that we will carry through this chapter is that rigid bodies are point masses or particles, and that all forces on the body have the same point of application. Obviously, this is not completely relative to real-life situations, but in order to simplify our calculations, we will assume that effects of forces acting on the body are not affected by any changes in the dimension or shape. So if we have a situation in which in real life there would be some type of deformation in an object relative to the situation, for our calculations and our problem sets, we will assume that that deformation does not occur, to more simply calculate forces that act on certain segments or certain masses. Forces can be classified into either internal forces or external forces, and internal forces are pairs of forces acting within an object or a system, and each force affects the object that it acts on, but does not affect the motion of the body. So it does not affect the motion of the body. Two specific types of internal forces are tensile forces and compressive forces. Tensile forces occur when there's pulling apart or tension, so the forces are going in opposite direction apart from one another, and compressive forces are forces that are again going in the opposite direction but compressing in towards one another. External forces act on an object or a system through interaction with the surrounding environment. So we have three different types of external forces that we were talking about. Contact force, which is when an object touches something else. Non-contact force is between objects not touching one another. And gravitational force, which is relative to strictly the weight of the object. Now, weight of an object is considered a non-contact force because it is the relationship between the mass of the object and the acceleration due to gravity. So weight, as you know at this point, is W equals mass times acceleration due to gravity. So this is a good example of a non-contact force in that these force pairs are not touching one another. So the mass of the object and gravity itself is not touching one another. However, it does produce some type of movement. If you take the example of this basketball player, when she jumps up into the air, right, gravity is the force acting on her to come back down. So when she is up in the air, she cannot necessarily change her projectile motion that she will go through. Obviously, we know that very elite athletes can move their body in space as they're in the air. However, gravity, which is a non-contact force acting on her as an object, will influence her parabolic path and cause her to come back down to the ground. Now, contact forces, as I briefly discussed, are forces that occur between objects that are touching one another. So each force acts separately on one of the objects, and this can also be termed reaction forces. Contact forces can be resolved into two primary components. One is the normal force, and the second is a parallel contact force. Normal contact force is the force that is perpendicular to two objects in contact. So if we have a box, again, sitting on a floor, the mass of this object is actually going to be its normal contact force because it is perpendicular to the object and the table that it is sitting on in parallel. Now, a parallel contact force is going to be, in this example, the force of friction, because in this case, friction is going to be acting in parallel manner between the box and the tabletop. Given this example of a runner's foot, the normal contact force is going to be the ground reaction force imparted as the mass of the runner comes downward. The normal contact force is again the ground reaction force going upward, while the friction force is going to be in the positive x direction as he or she is pushing backwards. So in this case, our normal contact is again perpendicular to the surface with the mass of the runner coming down, where our friction or parallel force is, of course, in parallel between the objects that are in contact with one another. Friction itself is the force that occurs in opposing sliding or motion between objects in contact. It does result from interaction between surface molecules. And there are two main types of friction: static friction and dynamic friction. Static friction occurs where two surfaces are not moving on one another. And one important component of static friction is what's called limiting friction, which is the amount of friction that must be overcome before an object can start to slide on another object. Dynamic friction is when two surfaces are moving on one another, of course in opposite directions, right? And this is also known as sliding friction or kinetic friction. Friction is proportional to the force pushing the two surfaces together. This is mathematically represented by the symbol R, and a greater R is therefore going to equal a greater friction. So if we go back to our box example, if we think about point of contact, if we're trying to move this box in the positive x direction, if R is represented by the force pushing surfaces together, a force application at this angle is actually going to create a greater R because there's more force pushing these objects together rather than a force coming directly parallel to the surface that the box is sliding on. Friction itself is also affected by characteristics of two materials in contact, and this is called the coefficient of friction and is represented by the Greek letter mu right here. Friction is mathematically represented by F equals mu times R, where mu is the standard coefficient of friction that is based on the material itself. So all materials have a regulated coefficient of friction number, and then that will be multiplied by the quantity of the normal contact force.